Has anyone in here ever worked with libUSB or PyUSB? Hands up. Okay. Who also thinks USB is a pain? Okay. Sergey and Alexander were here back at the 2063. That's a long time ago. I think it was back in Berlin. And back then they presented their first homemade, or not homemade, SDR, software-defined radio. This year, they are back again, and they want to show us how they implemented another one using an FPGA, and to communicate with it, they used PCI Express. So I think if you thought USB was a pain, let's see what they can tell us about PCI Express. A warm round of applause for Alexander and Sergey for building a high-throughput, low-latency, PCIe-based software-defined radio.
Hi, everyone. Good morning, and welcome to the first day of the Congress. So, just a little bit background about what we've done previously and why we are doing what we are doing right now is that we started working with software-defined radios. And by the way, who knows what software-defined radio is? Okay. Perfect. And whoever actually used the software-defined radio is RTL SDR or, okay, less people, but still quite a lot. Okay, good. I wonder whether anyone here used more expensive radios like USERPs? Less people, but few. Okay, good. Cool. So, before 2008, I had no idea what software-defined radio is, was working with voice over IP, a software person, etc., etc. So in 2008, I heard about OpenBTS, got introduced to software-defined radio, and I wanted to make it really work. And that's what led us to today. In 2009, we had to develop a clock tamer, a hardware which allowed to use USERP1 to run GSM without problems. If anyone ever tried doing this without a good clock source, knows what I'm talking about. And we presented this. It wasn't really an SDR; it was just a clock source. We presented this in 2009 in 2063, then we realized that using USERP1 is not really a good idea because we wanted to build a robust industrial-grade base stations. So we started developing our own software-defined radio, which we call Umtrix. And it was in 2000. We started this in 2011. Our first base stations were deployed in 2013, but I always wanted to have something really small and really inexpensive. And back then, it wasn't possible. My original idea in 2011 were to build a PCI Express card. Not PCI Express card, but mini PCI card. If you remember, there were all the Wi-Fi cards in mini PCI form factor, and I thought that would be really cool to have an SDR in mini PCI, so I can plug this into my laptop or in some embedded PC and have a nice SDR equipment. But back then, it just was not really possible because electronics were bigger and more power hungry, and just didn't work that way. So we designed Umtrix to work over gigabit Ethernet, and it was about that size. So now we spent this year designing something which really brings me to what I wanted those years ago. So the Xtrix is a mini PCI Express. Again, there was no PCI Express back then, so now it's mini PCI Express, which is even smaller than PCI, mini PCI. And It's built to be embedded friendly, so you can plug this into a single board computer, embedded single board computer. If you have a laptop with a mini PCI Express, you can plug this into your laptop, and you have a really small software-defined radio equipment. And we really want to make it inexpensive. That's why I was asking how many of you have ever worked with RTL SDR, how many of you ever worked with usurps, because the gap between them is pretty big. And we want to really bring the software-defined radio to masses. Definitely won't be as cheap as RTL SDR, but we try to make it as close as possible. And at the same time, so at the size of RTL SDR, at the price well higher, but hopefully it will be affordable to pretty much everyone, we really want to bring high performance into your hands. And by high performance, I mean this is a full transmit receive with 2 channels transmit, 2 channels receive, which is usually called 2x2 MIMO in the radio world. The goal was to bring it to 160 megasamples per second, which can roughly give you like 120 megahertz of radio spectrum available. So what we were able to achieve is, again, this is mini PCI Express form factor. It has small Arctic 7, that's the smallest and most inexpensive FPGA, which has ability to work with a PCI Express. It has LMS 7000 chip for RFIC. It's very high performance, very tightly tightly embedded chip with even a DSP blocks inside. It has even a GPS chip here. Do you see my screen? No, you can't see it, but so it has, you can actually, on the right upper side, you can see a GPS chip. So you can actually synchronize your SDR to GPS for perfect clock stability. So you won't have any problems running any telecommunication systems like GSM, 3G, 4G due to clock problems. And it also has interface for SIM cards, so you can actually create a software-defined radio modem, and there are already open source projects to build one for LTE called SRS-UE if you're interested, etc., etc. So it's really, really tightly packed one. And if you put this into perspective, that's how it all started in 2006, and that's what you have 10 years later. It's pretty impressive. So, thanks. But I think it's actually applause to the whole industry who is working on shrinking the sizes, because we just put stuff on the PCB. You know, we are not building the silicon itself. Interesting thing is that we did the first approach. We said, let's pack everything. Let's do a very tight PCB design. We did an 8-layer PCB design. And when we send it to a fab to estimate the cost, it turned out it's $15,000 per piece. Well, in small volumes, obviously, but still a little bit too much. So we had to redesign this. And the first thing which we did is we still kept 8 layers, because in our experience, number of layers nowadays have only minimal impact on the cost of the device. So like 6, 8 layers, the price difference is not so big. But we did complete rerouting and only kept 2 deep microvias and never used the buried vias. So this make it much easier and much faster for the fab to manufacture it. And the price suddenly went 5-6 times down. And in volume, again, it will be significantly cheaper. And that's just for geek porn how PCB looks inside. So now let's go into real stuff. So PCI Express, why did we choose PCI Express? As it was said, USB is a pain in the ass. You can't really use USB in industrial systems for a whole variety of reasons, just unstable. So we did use Ethernet for many years successfully, but Ethernet has one problem. First of all, inexpensive Ethernet is only 1 gigabit, and 1 gigabit does not offer you enough bandwidth to carry all the data we want. Plus, it's power hungry, etc., etc. So PCI Express is really a good choice because it's low power, it has low latency, it has very high bandwidth, and it's available almost universally. When we started looking into this, we realized that even ARM boards, some of ARM boards have mini PCI Express slots, which was a big surprise for me, for example. So the problems is that unlike USB, you do need to write your own kernel driver for this. And there is no way around. And it is really hard to write this driver universally, so we are writing it obviously for Linux because we're working with embedded systems, but if we want to rewrite it for Windows or for macOS, we'll have to do a lot of rewriting. So we focus on what we want on Linux only right now. And now the hardest part, debugging is really non-trivial. One small error and your PC is completely hang because you did something wrong. And you have to reboot it and restart it. And that's like debugging kernel, but sometimes even harder. So, and to make it worse, there is no really easy to use plug and play interface. So if you want to restart, normally when you develop a PCI Express card, when you want to restart it, you have to restart your development machine. Again, not a nice way. It's really hard. So the first thing we did is we found that we can use Thunderbolt 3, which is just recently released, and it has ability to work directly with PCI Express bus. So it basically has a mode in which it converts a PCI Express into plug-and-play interface. So if you have a laptop which supports Thunderbolt 3, then you can use this to plug and play plug or unplug your device to make your development easier. There are always problems. There's no easy way. There's no documentation. Thunderbolt is not compatible with Thunderbolt. Thunderbolt 3 is not compatible with Thunderbolt 2. So we had to buy a special laptop with Thunderbolt 3 with special cables, like all this hard stuff. And if you really want to get documentation, you have to sign NDA and send a business plan to them so they can approve that your business makes sense. I mean, so we actually opted out. We decided not to go through this. What we did is we found that someone is actually making PCI Express or Thunderbolt 3 converters and selling them as dev boards. And that was a big relief because it saved us lots of time, lots of money. We just ordered it from some Asian company. And yeah, this is how it looks like, this converter. So you buy it like several pieces. You can plug in your PCI Express card there, and you plug this into your laptop. And this is with XTRX already plugged into it. Now, the only problem we found is that typically UEFI has security control enabled, so that any random Thunderbolt device can't hijack your PCI bus and can't get access to your kernel memory and do some bad stuff, which is a good idea. The only problem is that it's not fully implemented in Linux. So under Windows, if you plug in a device which has no security features, which is not certified, then it will politely ask you, like, do you really trust this device? Do you want to use it? You can say yes. Under Linux, it just does not work. So we spent some time trying to figure out how to get around this. There are some patches from Intel which are not mainlined, and we were not able to actually get them work. So we just had to disable this security measure in the laptop. So be aware that this is the case. And we suspect that happy users of Apple might not be able to do this because Apple don't have BIOS, so you probably can't disable this feature. So probably a good incentive for someone to actually finish writing the driver. So now to the goal. So we want to achieve 160 megasamples per second 2x2 MIMO, which means to transceive, to transmit, to receive channels at 12 bits, which is roughly 7.5 gigabit per second. So first result, when we got this board from the fab, it didn't work.
As expected.
Yeah, as expected. So the first interesting thing we realized is that, well, first of all, the FPGA has hardware blocks for talking to a PCI Express, which called GTP, which basically implement like a PCI Express serial physical layer. But the thing is, the numbering is reversed in PCI Express in FPGA, and we didn't realize this. So we had to do very, very fine soldering to actually swap the lanes. You can see this very fine work there. We also found that one of the components was dead bug, which is a well-known term for chips which at design stage are placed mirrored. So we mirrored, occasionally mirrored the pinout. So we had to solder it upside down. And if you can realize how small it is, you can also appreciate the work done. And what's funny, when I was looking at the dead bugs, I actually found a manual from NASA which describes how to properly solder dead bugs to get it approved. So this is a link. I think you can go there and enjoy. There's lots of fun stuff there. So after fixing all of this, our next attempt kind of works. So next stage is debugging the FPGA code, which has to talk to PCI Express, and PCI Express has to talk to Linux kernel. Linux kernel has to talk to the driver. Driver has to talk to the user space. So peripherals are easy. So all the UART, SPIs, we've got to work almost immediately. No problems with that. But DMA was a real beast. So we spent lots of time trying to get DMA to work. And the problem is that with DMA, it's on an FPGA, so you can't just place a breakpoint like you do in C or C++ or any other languages. It's a real-time system running, not system, like it's real-time hardware which is running on the fabric. So we had to, Sergey, who was mainly developing this, had to write a lot of small test benches and test everything piece by piece. So all parts of the DMA code we had was wrapped into a small test bench which was emulating all the tricks. And as classics predicted, it took about 5 to 10 times more than actually writing the code. So we really blew up our predicted timelines by doing this, but at the end we've got really stable work. So some suggestions for anyone who will try to repeat this exercise is there is a logic analyzer built into Xilinx, and you can use it. It's nice. It's sometimes it's very helpful, but you can't debug transient bugs which are coming out when some weird conditions are coming up. So you have to implement some readback registers, which shows important important data about how your system behaves. In our case, it's various counters on the DMA interface, so you can actually see, kind of see what's happening with your data. Is it received? Is it sent? How much is sent? How much is received? So, like for example, we can see when we saturate the bus, or when actually there's an underrun, so the host is not providing data fast enough, so we can at least understand whether it's a host problem or whether it's an FPGA problem, on which part should we debug next. Because again, it's a very multi-layer problem. We start with FPGA, PCI Express, kernel, driver, user space, and any part can fail. So you can't work blind like this. So again, the goal was to get 160 megasamples. With the first naive implementation, we got 2 megasamples per second, roughly 60 times slower. The problem is that software just wasn't keeping up and wasn't sending data fast enough. So there was like many things done, but the most important parts is use real-time priority if you want to get very stable results. And, well, fix software bugs. And one of the most important bugs we had was that DMA buffers were not freed in proper time immediately. So they were busy for longer than they should be, which introduced extra cycles and basically just reduced the bandwidth. So at this point, let's talk a little bit about how to implement a high-performance driver for Linux, because if you want to get real performance, you have to start with the right design. So there are basically 3 approaches and the whole spectrum in between, like 2 approaches and the whole spectrum in between, which you can refer to 3. So the first approach is full kernel control, in which case kernel driver not only is doing the transfer, it actually has all the logics of controlling your device and only export IOKTL to the user space. And that's the kind of a traditional way of writing drivers. Your user space is completely abstracted from all the details. Well, the problem is that this is probably the slowest way to do it. So the other way is what's called the zero-copy interface, where only control is held in the kernel and data is provided, raw data is provided to user space as is. So you avoid the memory copy, which make it faster, but still not fast enough if you really want to achieve maximum performance, because you still have context switches between the kernel and the user space. So the fastest approach possible is to have full user space implementation, when kernel just exposes everything and says, now you do it yourself, and you have no context switches, like almost no, and you can really optimize everything. So what are the problems with this? The pros I already mentioned: no switches between kernel and user space. It's very low latency because of this as well. It's very high bandwidth. But if you are not interested in getting the very high performance, the most performance, and you just want to have like some say low bandwidth performance, then you will have to add hacks, because you can't get notification from the kernel that resources available, which is more data available. So it also makes it vulnerable, because if user space can access it, then it can do whatever it wants. So we, at the end, decided, so one more important thing. So how to actually get the best performance out of the bus. And this is where you have to decide whether you want to poll your device or not to poll or get notified. So what is polling? I guess everyone as programmer understands it. So polling is when you ask repeatedly, are you ready? Are you ready? Are you ready? And when it's ready, you get the data immediately. So it's basically a busy loop of you're just constantly asking device what's happening. And you need to dedicate a full core, and thanks God we have multi-core CPUs nowadays, so you can dedicate the full core to this polling, and you can just poll constantly. But again, if you don't need this highest performance, you just need to get something, then you will be wasting a lot of CPU resources. So at the end, we decided to do a combined architecture where it is possible to poll, but there is also a chance to get notification from a kernel for applications which need low bandwidth, but also require a better CPU performance, which I think is the best way if you're trying to target both worlds. So very quickly, so the architecture of the system. So we tried to make it very, very portable, and flexible. So there is a kernel driver. There is a kernel driver which talks to a low-level library which implements all this logic which we took out of the driver to control the PCI Express, to work with DMA, to provide to hide all the details of the actual bus implementation. And then there is a high-level library which talks to this low-level library and also to libraries which implement control of actual peripherals, and most importantly to the library which implements control over our RFIC chip. So this way, it's very modular. We can replace PCI Express with something else later. We might be able to port it to other operating systems. And that's the goal. Another interesting issue is when you start writing a Linux kernel driver, you very quickly realize that while LDD, which is a classic book for Linux driver writing, is good and it will give you a good insight, it's not actually up to date. It's more than 10 years old, and there's a lot of new interfaces which are not described there. So you have to resort to reading the manuals and all the documentation in the kernel itself. Well, at least you get the up-to-date information. So the decisions we made is to make everything easy. So we use TTY for GPS, and so you can really attach pretty much any application which talks to GPS. All of existing applications can just work out of the box. And we also wanted to be able to synchronize system clock to GPS. So we get automatic log synchronization across multiple systems, which is very important when we are deploying many devices around the world. So we plan to do two interfaces. One is key PPS, and another is a DCD, because a DCD line on the UART exposed over TTY. So because again, we found that there are two types of applications, one that support one API and others that support other API, and there is no common thing, so we have to support both. What's interesting else is that, as we described, we want to have polls so we can get notifications from the kernel when data is available, and we don't need to do real busy looping all the time. So after all the software optimizations, we've got to 10 megasamples per second. Still very far from what we want to achieve. Now there should have been a lot of explanations about PCI Express, but when we actually wrote everything we wanted to say, we realized it's just like a full 2 hours talk just on PCI Express. So we are not going to give it here. I'll just give some highlights which are most interesting. If there's real interest, we can set up a workshop at some of the later days and talk in more details about PCI Express specifically. So the thing is, there is no open source cores for PCI Express which are optimized for high performance real-time applications. There is Xalibus, which, as I understand, is not really open source, but they provide you a source if you pay them. But it's very popular because it's very, very easy to do, but it's not giving you performance. If I remember correctly, the best it can do is maybe like 50% bus saturation. So there is also Xilinx implementation, but if you're using Xilinx implementation with XZI bus, then you're really locked in with XZI bus, with Xilinx, and it also not very efficient in terms of resources. And if you remember, we want to make this very, very inexpensive. So our goal is to be able to fit everything in the smallest Arctic 7 FPGA. And that's quite challenging with all the stuff in there. And we just can't waste resources. So decision is to write your own PCI Express implementation. That's how it looks like. We're not going to discuss it right now. There were several iterations. Initially, it looked much simpler. Turned out not to work well. So, some interesting stuff about PCI Express, which we stumbled upon, is that it was working really well on Atom, which is our main development platform because we are doing a lot of embedded stuff. Worked really well when we tried to plug this into Core i7, just started hanging once in a while. So after like several days maybe of debugging, Sergey found that there's a very interesting statement in the standard which says that value 0 in byte count actually stands not for 0 bytes, but for 4096 bytes. I mean, that's a really cool optimization. So another thing is completion, which is a term in PCI Express basically for acknowledgement, which also can carry some data back to your request. And sometimes if you're not sending completion, device just hangs. And what happens is that in this case, due to some historical heritage of x86, it just starts returning you FFF. And if you have a register which says, is your device okay? And this register shows 1 to say the device is okay, guess what will happen? You will be always reading that your device is okay. So the suggestion is not to use 1 as a status for OK and use either 0 or better like a 2-bit sequence. So you definitely sure that you are OK and not getting FFFs. So when you have a device which, again, may fail at any of the layers, you just got this new board, it's really hard. It's really hard to debug, and there's a lot of memory corruption. So we had a software bug, and it was writing DMA addresses incorrectly. And we were wondering why we are not getting any data in our buffers. At the same time, after several starts, operating system just crashes. Well, that's the reason why there is this UEFI protection which prevents you from plugging in devices like this into your computer, because it was basically writing data, like random data, into random portions of your memory. So a lot of debugging a lot of tests and test benches, and we were able to find this. And another thing is, if you deinitialize your driver incorrectly, and that's what's happening when you have plug-and-play device, which you can plug and unplug, then you may end up in a situation where you are trying to write into memory which is already freed by operating system and used for something else. Very well-known problem, but also happens here. So why DMA is really hard is because it has this completion architecture for writing, for reading data. Writes are easy. You just send the data, you forget about it. It's fire and forget system. But for reading, you really need to get your data back. And the thing is, it looks like this. I really hope that there would be some pointing device here. But basically, on the top left, you can see requests for read. And on the right, you can see completion transactions. So basically, each transaction can be, and most likely will be, split into multiple transactions. So first of all, you have to collect all these pieces and write them into proper parts of the memory. But that's not all. The thing is, the latency between request and completion is really high. It's like 50 cycles. So if you have only single transaction in fly, you will get really bad performance. You do need to have multiple transactions in flight. And the worst thing is that transactions can return data in a random order. So it's a much more complicated state machine than we expected originally. So when I said, our architecture was much simpler originally, we did not have all of this, and we had to realize this while implementing. So again, here was a whole description of how exactly this works, but not this time. So now, after all these optimizations, we got 20 megasamples per second, which is just 6 times lower than what we are aiming at. So now, the next thing is PCI Express lane scalability. So PCI Express is a serial bus, so it has multiple lanes, and they allow you to basically horizontally scale your bandwidth. One lane is like X, then 2 lane is 2X, 4 lane is 4X. So the more lanes you have, the more performance you're getting out of your bus. So the more bandwidth you get out of your bus, not performance, but. So the issue is that a typical mini PCI Express, so the mini PCI Express standard only standardize one lane, and second lane is left as optional. So most motherboards don't support this. There are some, but not all of them. And we really wanted to get this done, so we designed a special converter board which allows you to plug your mini PCI Express into a full-size PCI Express and get two lanes working. And we're also planning to have a similar board which will have multiple slots, so you will be able to get multiple Xtrix SDRs onto the same carrier board and plug this into, let's say, PCI Express 16X. And you will get like really a lot of SDR, really a lot of IQ data, which then will be your problem how to process. So with 2X's, it's about twice performance, so we are getting 50 megasamples per second. And that's the time to really cut the fat, because the real sample size of LMS7 is 12 bits. And we are transmitting 16 because it's easier, because CPU is working on 8, 16, 32. So we originally designed the driver to support 8-bit, 12-bit, and 16-bit to be able to do this scaling. And for the test, we said, okay, let's go from 16 to 8-bit. We'll lose some dynamic range, but who cares these days? Still stayed the same. It's still 50 megasamples per second, no matter what we did. And that was a lot of interesting debugging going on, and we realized that we actually made another, not a really mistake. We didn't really know this when we designed, but we should have used a higher voltage for this high-speed bus to get it to the full performance. And at 1.8, it was just degrading too fast, and the bus itself was not performing well. So our next prototype will be using higher voltage specifically for this bus. And this is kind of stuff which makes designing hardware for high speed really hard, because you have to care about the coherence of the parallel buses on your system. So at the same time, we do want to keep 1.8 volt for everything else as much as possible, because another problem we are facing with this device is that by the standard mini PCI Express allows only like 2.5 watts of power consumption, no more. And that's where we were very lucky that LMS7 has like so good power consumption performance. We actually had some extra space to have FPGA and GPS and all this stuff, but we just can't let the power consumption go up. Our measurements on this device showed about like 2.3 watts of power consumption, so we are like at the limit at this point. So when we fixed the bus with a higher voltage, again, now it's a theoretical exercise because we haven't done this yet. It's planned to happen in a couple of months. We should be able to get to this number, which is just 1.2 times slower. And then the next thing will be to fix another issue which we made at the very beginning. We procured a wrong chip. So just one digit difference. You can see it's selected, highlighted in red and green. And this chip supports only Generation 1 PCI Express, which is twice slower than Generation 2 PCI Express. So again, hopefully we'll replace the chip and just get very simple doubling of the performance. Still, it will be slower than we wanted it to be. And here is what comes like practical versus theoretical numbers. Well, as every bus, it has overheads. And one of the things which, again, we realized when we were implementing this is that even though the standardizes the payload size of 4 kilobytes, actual implementations are different. For example, desktop computers like Intel Core or Intel Atom, they only have 128-byte payload, so there is much more overhead going on the bus to transfer data, and even theoretically, you can only achieve 87% efficiency. And on Xeon, we tested and we found that they're using 256 payload size, and this can give you like a 92% efficiency on the bus. And this is before the overhead, so the real reality is even worse. An interesting thing, which we also did not expect, is that we originally were developing on Intel Atom, and everything was working great. When we plugged this into a laptop like Core i7, multi-core, really powerful device, we didn't expect that it wouldn't work. Obviously, like Core i7 should work better than Atom. No, not always. The thing is, we were plugging into a laptop which had a built-in video card, which was sitting on the same PCIe bus, and probably manufacturer hard-coded higher, what's called higher. Forgot the word priority. Yes, a higher priority for the video card than for everything else in the system, because you don't want your screen to flicker. And so when you move a window, you actually see their late packets coming to your PCI device. We had to introduce a jitter buffer and add more FIFO into the device to smooth it out. And on the other hand, Xeon is performing really well. So it's very optimized. That said, we tested it with discrete card, and outperforms everything by a whooping 5-7%. It's what you get for the price. So this is actually the end of the presentation. We still have not scheduled any workshop, but if there's any interest in actually seeing the device working, or if you're interested in learning more about the PCI Express in details, let us know. We'll schedule something in the next few days. That's it, and I think we can proceed with questions if there are any.
Okay. Thank you very much. If you are leaving now, please try to leave quietly, because we might have some questions and we want to hear them. And if you have questions, please line up right behind the microphones. And I think we'll just wait, because we don't have anything from the Signal Angel. However, if you're watching on stream, you can hop into the channels and over social media to ask questions, and they will be answered, hopefully. So, that microphone.
Yeah. What's the minimum and maximum frequency of the card?
You mean RF frequency?
And now the minimum frequency you can sample at. Most RTL SDR devices can only sample at over 50 megahertz. Is there a similar limitation at your card?
Yeah, so if you're talking about RF frequency, it can go from like almost zero, even though that works below 50 megahertz, and all the way to 3.8 gigahertz, if I remember correctly. Yeah, and in terms of the sample rate, right now it works from like about 2 megasamples per second, and all to about 50 right now, but again, we're planning to get it to these numbers we quoted.
Okay, the microphone over there.
Thanks for your talk. Did you manage to put your Linux kernel driver to the main line?
Oh, not yet. I mean, it's not even it's not even like fully published. So I did not say in the beginning. Sorry for this. We only just manufactured the first prototype, which we debugged heavily. So we are only planning to manufacture the second prototype with all these fixes, and then we will release like the kernel driver and everything. And I'm not sure maybe we'll try or maybe won't try. Haven't decided yet.
Thanks.
Okay, and
but
over
that
here
will be the
again?
whole other experience.
Okay, over there.
Hey, looks like you went through some incredible amounts of pain to make this work. So I was wondering, aren't there any simulators, at least for parts of the system, for the PCIe bus, for the DMA, something? Any simulators so that you can actually first design the system there and debug it more easily, you know?
Yeah, there are available simulators, but the problem, so they are non-free, so you have to pay for them. So, yeah. And we choose the hard way.
Okay, thanks.
Okay, we have a question from the Signal Angel.
Yeah, are the FPGA code, Linux driver, and library code and the design project files public? And if so, did they post them yet? Did we have posted them yet? They can't find them on xtirx.io.
Yeah, so they're not published yet. As I said, we haven't released them. The drivers and libraries will definitely available. FPGA code we are considering it probably also will be available in open source, but we will publish them together with the public announcement of the device.
Okay, that microphone.
Yes, did you guys see any signal integrity issues between on the PCI bus or on this bus to the LMS chip, the line micro chip? I think that's doing the RF. Right. Did you try to measure signal integrity issues, or because there were some reliability issues, right?
Yeah, we actually with PCI we never had issues, if I remember correctly. No. It was just working.
Actually, the board is so small. Mm-hmm. And when there is small traces, there's no problem in signal integrity, so it's actually save us.
Yeah, designing a small board is easier. Yeah, with LMS7, the problem is not the signal integrity in terms of difference in the length of the traces, but rather the fact that the signal degrades over voltage, over speed. In terms of voltage, and drops below the detection level and all this stuff. We did some measurements. I actually wanted to add some pictures here, but decided that's not going to be super interesting.
Okay, microphone over there.
Yeah, thanks for the talk. How much work would it be to convert the 2x2 SDR into an 8-input logic analyzer in terms of hardware and software? So to have a really fast logic analyzer where you can record unlimited traces with.
Logic analyzer.
So basically, it's just also an analog digital converter, and you largely want fast sampling and a large amount of memory to store the traces.
Well, I just think it's not the best use for it. It's probably I don't know. Maybe Sergey has any ideas, but I think it's just maybe easier to get a high-speed ADC and replace the Lime chip with a high-speed ADC to get what you want, because the Lime chip has so many things there specifically for RF.
Yeah, the main problem, you cannot just sample original data. You should shift it over frequency, so you cannot sample original signal. And using it for something else except spectrum analyzing is hard.
Okay, thanks.
Okay, another question from the internet.
Yes, have you compared the sample rate of the ADC of the LimesDR chip to the USRP ADCs? And if so, how does the lower sample rate affect the performance?
So, comparing low sample rate to high sample rate, we have not done many testing we haven't done much testing on the RF performance yet, because we were so busy with all this stuff. So, we are yet to see in terms of low bit rates versus sample rate versus high sample rate. Well, high sample rate always gives you better performance, but you also get higher power consumption. So I guess it's the question of what's more important for you.
Okay, over there.
I've gathered there is no mixer bypass, so you can't directly sample the signal. Is there a way to use the same antenna for send and receive yet? Or,
well, actually, there is input for ADC.
But it's not a bypass, it's a dedicated pin on a LMS chip, and since we are very space constrained, we didn't route them, so you cannot actually bypass it.
Okay.
In our specific hardware. So in general, so in the LMS chip, there is a special, again, like to rephrase, a special pin which allows you to drive your signal directly to ADC without all the mixers, filters, all this radio stuff, just directly to ADC. So yes, theoretically that's possible.
We even thought about this, but it doesn't fit this design.
Okay. And can I share antennas? Because I have an existing laptop with existing antennas, so but I would use the same antenna for send and receive.
Yeah. So I mean, that's depends on like what exactly do you want to do. If you want a TDD system, then yes. If you want an FDD system, then you will have to put a small duplexer in there. But yeah, that's the idea. So you can plug this into your laptop and use your existing antennas. That's one of the ideas of how to use Xtrix.
Yeah, because there's all 4 connectors.
Yeah, and one thing which I actually forgot to mention is, like I kind of mentioned in the slides, is that any other SDRs which are based on Ethernet or on the USB can't work with a CSMA wireless systems. And the most famous CSMA system is Wi-Fi. So turns out that because of the latency between your operating system and your radio on USB, you just can't react fast enough for Wi-Fi to work, because probably you know that in Wi-Fi you carrier sense, and if you sense that the spectrum is free, you start transmitting. Doesn't make a sense when you have huge latency, because you all know that the spectrum was free back then. So with Xtrix, you actually can work with CSMA systems like Wi-Fi. So again, it makes it possible to have a fully software implementation of Wi-Fi in your laptop. It obviously won't work like as good as your commercial Wi-Fi, because you will have to do a lot of processing on your CPU. But for some purposes, like experimentation, for example, for wireless labs and R&D labs, that's really valuable.
Thanks.
Okay, over there.
Okay, what PCB design package did you use?
Altium.
Okay.
Altium, yeah.
And I'd be interested in the PCI Express workshop. Would be really great if you do this one.
Sorry, second?
Would be really great if you do the PCI Express workshop.
PCI Express workshop. Okay, thank you.
Okay, I think we have one more question from the microphones, and that's you.
Okay, great talk, and again, I would appreciate the PCI workshop if it ever happens. What are the synchronization options between multiple cards? Can you synchronize the ADC clock, and can you synchronize the presumably digitally created IF?
Yes,
So unfortunately, just IF synchronization is not possible, because Lime chip doesn't expose a low frequency, but we can synchronize digitally. So we have special 1 PPS signal synchronization, we have lines for clock synchronization, and other stuff we can do in software. So the Lime chip has phase correction register. So when you measure phase difference, so you can compensate it on different boards.
So tune to a station a long way away and then rotate the phase until it aligns.
Yeah.
Right.
Thank you.
Yeah, it's a little tricky, but possible. So that's one of our plans for future, because we do want to see like 128 by 128 MIMO at home.
Okay, we have another question from the internet.
I actually have two questions. The first one is, what is the expected price after a prototype stage? And the second one is, can you tell us more about the setup you had for debugging the PCIe issues?
So could you repeat the second question?
It's setup debug.
More about the setup you had for debugging the PCIe issues.
Second question, I think it's most about our next workshop, because it's a more complicated setup, so we mostly remove everything about it in our current presentation.
Yeah, but in general, I mean, in terms of hardware setup, that was our hardware setup. So we bought this PCI Express to Thunderbolt 3. We bought a laptop which supports Thunderbolt 3, and that's how we were debugging it. So we don't need like a full-fledged PC. We don't have to restart it all the time. So in terms of price, we don't have their like fixed price yet. So all I can say right now is that we are targeting no more than your like BladeRF or HackerRF devices, and probably even cheaper for some versions.
Okay, we are out of time. So thank you again, Sergey and Alexander.